Chapter 7 Transactions. Some authors have claimed that general two-phase commit is too expensive to support because of the performance or availability problems that it brings. We believe it is better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks arise, rather than always coding around the lack of transactions. James Corbett et al. Thanner, Google's Globally Distributed Database 2012. In the harsh reality of data systems, many things can go wrong. The database software or hardware may fail at any time, including in the middle of a write operation. The application may crash at any time, including halfway through a series of operations. Interruptions in the network can unexpectedly cut off the application from the database, or one database node from another. Several clients may write to the database at the same time, overwriting each other's changes. A client may read data that doesn't make sense because it has only partially been updated. Race conditions between clients can cause surprising bugs. In order to be reliable, a system has to deal with these faults and ensure that they don't cause catastrophic failure of the entire system. However, implementing fault tolerance mechanisms is a lot of work. It requires a lot of careful thinking about all the things that can go wrong, and a lot of testing to ensure that the solution actually works. For decades, transactions have been the mechanism of choice for simplifying these issues. A transaction is a way for an application to group several reads and writes together into a logical unit. Conceptually, all the reads and writes in a transaction are executed as one operation. Either the entire transaction succeeds commit or it fails abort. Rollback. If it fails, the application can safely retry. With transactions, error handling becomes much simpler for an application because it doesn't need to worry about partial failure, i.e. the case where some operations succeed and some fail for whatever reason. If you have spent years working with transactions, they may seem obvious, but we shouldn't take them for granted. Transactions are not a law of nature. They were created with a purpose, namely to simplify the programming model for applications accessing a database. By using transactions, the application is free to ignore certain potential error scenarios and concurrency issues, because the database takes care of them. Instead, we call these safety guarantees. Not every application needs transactions, and sometimes there are advantages to weakening transactional guarantees or abandoning them entirely, for example, to achieve higher performance or higher availability. Some safety properties can be achieved without transactions. How do you figure out whether you need transactions? In order to answer that question, we first need to understand exactly what safety guarantees transactions can provide, and what costs are associated with them. Although transactions seem straightforward at first glance, there are actually many subtle but important details that come into play. In this chapter, we will examine many examples of things that can go wrong, and explore the algorithms that databases use to guard against those issues. We will go especially deep in the area of concurrency control, discussing various kinds of race conditions that can occur and how databases implement isolation levels such as read committed, snapshot isolation, and serializability. This chapter applies to both single-node and distributed databases. In Chapter 8 we will focus the discussion on the particular challenges that arise only in distributed systems. The slippery concept of a transaction. Almost all relational databases today, and some non-relational databases, support transactions. Most of them follow the style that was introduced in 1975 by IBM System R, the first SQL database. Although some implementation details have changed, the general idea has remained virtually the same for 40 years. The transaction support in MySQL, PostgreSQL, Oracle, SQL Server, etc. is uncannily similar to that of System R. In the late 2000s, non-relational NoSQL databases started gaining popularity. They aim to improve upon the relational status quo by offering a choice of new data models, see Chapter 2, and by including replication Chapter 5 and partitioning Chapter 6. By default, transactions were the main casualty of this movement. Many of this new generation of databases abandoned transactions entirely, or redefined the word to describe a much weaker set of guarantees than had previously been understood. With the hype around this new crop of distributed databases, there emerged a popular belief that transactions were the antithesis of scalability, and that any large-scale system would have to abandon transactions in order to maintain good performance and high availability. On the other hand, transactional guarantees are sometimes presented by database vendors as an essential requirement for serious applications with valuable data. Both viewpoints are pure hyperbole. The truth is not that simple. Like every other technical design choice, transactions have advantages and limitations. In order to understand those trade-offs, let's go into the details of the guarantees that transactions can provide both in normal operation and in various extreme, but realistic circumstances. Meaning of ACID. The safety guarantees provided by transactions are often described by the well-known acronym ACID, which stands for atomicity, consistency, isolation, and durability. It was coined in 1983 by Theo Heder and Andreas Reuter in an effort to establish precise terminology for fault tolerance mechanisms in databases. However, in practice, one database's implementation of ACID does not equal another's implementation. For example, as we shall see, there is a lot of ambiguity around the meaning of isolation. The high-level idea is sound, but the devil is in the details. Today, when a system claims to be ACID compliant, it's unclear what guarantees you can actually expect. ACID has unfortunately become mostly a marketing term. Systems that do not meet the ACID criteria are sometimes called BASE, which stands for basically available, soft state, and eventual consistency. This is even more vague than the definition of ACID. It seems that the only sensible definition of base is not ACID, i.e. it can mean almost anything you want. Let's dig into the definitions of atomicity, consistency, isolation, and durability, as this will let us refine our idea of transactions. In general, atomic refers to something that cannot be broken down into smaller parts. The word means similar but subtly different things in different branches of computing. For example, in multi-threaded programming, if one thread executes an atomic operation, that means there is no way that another thread could see the half-finished result of the operation. The system can only be in the state it was before the operation or after the operation, not something in between. By contrast, in the context of ACID, atomicity is not about concurrency. It does not describe what happens if several processes try to access the same data at the same time, because that is covered under the letter I. For isolation, see isolation on page 225. Rather, ACID atomicity describes what happens if a client wants to make several writes, but a fault occurs after some of the writes have been processed. For example, a process crashes, a network connection is interrupted, a disk becomes full, or some integrity constraint is violated. If the writes are grouped together into an atomic transaction, and the transaction cannot be committed due to a fault, then the transaction is aborted and the database must discard or undo any writes it has made so far in that transaction. Without atomicity, if an error occurs partway through making multiple changes, it's difficult to know which changes have taken effect and which haven't. The application could try again, but that risks making the same change twice, leading to duplicate or incorrect data. Atomicity simplifies this problem. If a transaction was aborted, the application can be sure that it didn't change anything, so it can safely be retried. The ability to abort a transaction on error and have all writes from that transaction discarded is the defining feature of ACID atomicity. Perhaps abortability would have been a better term than atomicity, but we will stick with atomicity since that's the usual word. The word consistency is terribly overloaded. In Chapter 5 we discussed replica consistency and the issue of eventual consistency that arises in a synchronously replicated system. See problems with replication lag on page 161. Consistent hashing is an approach to partitioning that some systems use for rebalancing. See consistent hashing on page 204. In the CAP theorem, see Chapter 9. The word consistency is used to mean linearizability. See linearizability on page 324. In the context of ACID, consistency refers to an application-specific notion of the database being in a good state. It's unfortunate that the same word is used with at least 4 different meanings. Joe Hellerstein has remarked that the C in ACID was tossed in to make the acronym work in Heder and Reuter's paper, and that it wasn't considered important at the time. The idea of ACID consistency is that you have certain statements about your data invariants that must always be true. For example, in an accounting system, credits and debits across all accounts must always be balanced. If a transaction starts with a database that is valid according to these invariants, and any writes during the transaction preserve the validity, then you can be sure that the invariants are always satisfied. However, this idea of consistency depends on the application's notion of invariance, and it's the application's responsibility to define its transactions correctly so that they preserve consistency. This is not something that the database can guarantee. If you write bad data that violates your invariants, the database can't stop you. Some specific kinds of invariants can be checked by the database, for example using foreign key constraints or uniqueness constraints. However, in general, the application defines what data is valid or invalid. The database only stores it. Atomicity, isolation, and durability are properties of the database, whereas consistency in the ACID sense is a property of the application. The application may rely on the database's atomicity and isolation properties in order to achieve consistency, but it's not up to the database alone. Thus, the letter C doesn't really belong in ACID.I. Most databases are accessed by several clients at the same time. That is no problem if they are reading and writing different parts of the database, but if they are accessing the same database records, you can run into concurrency problems. Race conditions. Isolation in the sense of ACID means that concurrently executing transactions are isolated from each other. They cannot step on each other's toes. The classic database textbooks formalize isolation as serializability, which means that each transaction can pretend that it is the only transaction running on the entire database. The database ensures that when the transactions have committed, the result is the same as if they had run serially one after another, even though in reality they may have run concurrently. Figure 7-1. A race condition between two clients concurrently incrementing a counter. However, in practice, serializable isolation is rarely used because it carries a performance penalty. Some popular databases, such as Oracle 11g, don't even implement it. In Oracle there is an isolation level called serializable, but it actually implements something called snapshot isolation, which is a weaker guarantee than serializability. We will explore snapshot isolation and other forms of isolation and weak isolation levels on page 233. The purpose of a database system is to provide a safe place where data can be stored without fear of losing it. Durability is the promise that once a transaction has committed successfully, any data it has written will not be forgotten, even if there is a hardware fault or the database crashes. In a single-node database, durability typically means that the data has been written to non-volatile storage such as a hard drive or SSD. It usually also involves a write-ahead log or similar C, making B trees reliable on page 82, which allows recovery in the event that the data structures on disk are corrupted. In a replicated database, durability may mean that the data has been successfully copied to some number of nodes. In order to provide a durability guarantee, a database must wait until these writes or replications are complete before reporting a transaction as successfully committed. As discussed in reliability on page 6, perfect durability does not exist. If all your hard disks and all your backups are destroyed at the same time, there's obviously nothing your database can do to save you.